Hello class, in this lesson we're going to be learning how to solve exponential and logarithmic equations. First try this by yourself. It should be something you can do. I'll show the answers right now. You notice that to do this was quite easy. All you did was either, because the bases were the same here, you set the exponents to be the same, and even in this case here you just created a little equation for yourself to solve for x. So either you set the exponents the same or you set the input into the logarithms the same when you had log base 2 and log base 2 on each side of the equation. So the key principle here is the following, that when you have an equation that looks like this, base to the x power is equal to base to the x power, or y power, then you know that x is equal to y. And similarly, when you had log base b of x is log base b of y, then you could also say that x is equal to y. This is, you could do this as long as the equation was, I'll say, simple enough, where the bases on each side were the same, and you didn't have a lot of other stuff on each side of the equation. These are very simple kind of equations here. We're going to step it up where we look at some other types of equations and see kind of the techniques in solving them. Two methods I'm going to be showing in this video here. Method 1, when the bases are not the same, make them the same. So when you have logs, say in this case here's a case where it's not just log equals log. We have log is equal to log plus a log. But we have rules, we have methods where we can actually condense the multiple logs into a single log term. So sometimes you need to use those log properties. Now with logarithms, when we solve, we need to make sure that because the domain of the log function must always be positive, we need to make sure that whatever solution that we find fits that. So remember that our log graph looks like this. The domain of the log graph is only numbers that are greater than 0, only positive numbers. So we cannot have any sort of x solution that is negative. Okay, now let's look at these couple of examples. I need to turn these into the same base. 27 is 3 to the third. Now we also know that this can be changed into 3 to the 3 times x minus 4, and then we can just set the exponents to be the same as each other, and then we could solve, and x is equal to 12. In this case, we have two log statements here, the sum of two logs, which we can turn into a single log by multiplying the two inputs together. So we have x times x plus 1. We multiply that together. Now we set the inputs the same because we have log base 2 on this side, log base 2 on this side. So I'm just going to set the inputs the same. We have x squared plus x is equal to x plus 4. Now the x's cancel out, and we find that x squared is 4, but that means that x could be 2 or negative 2, but again, remember, we need to check our answers. Negative 2 is not a solution. If we were to plug negative 2 into the very original equation up here, we get this down here. Now, negative 2 could be a solution to a logarithm equation. Negative 2 by itself does not rule out it being an answer. It's just that when we plug it in this case over here, it's less than 0. In this case over here, minus 2 plus 1, that's less than 0. So the logarithm input in these two instances here is negative. Over here, the input to the log is positive, so this part's okay. Nothing wrong on the left-hand side. It's these two pieces here where we have a negative input to a log and a negative input to a log. That invalidates the solution. Okay, so give these a try, and in 3, 2, 1, I'll show the solutions. Okay, moving on now. Method number 2. we want to use the inverse property of logarithms and exponents to solve equations sometimes. So in this case, we have 2 to the x is equal to 10, and it's not in this nice 2 to the x is equal to 2 to the something type of form. We don't have that in this case here, so we need a different mechanism. And in this case, the concept is to take either the log of both sides or to exponentiate both sides. So in this case, we have 2 to the x. We want to do the opposite of exponentiation, which is taking the log. We're going to choose log base 2 because this is already base 2. So log base 2 of both sides, and now these undo each other, so we get just x here. X is equal to log base 2 of 10. In this other case here, I have log base 2 as my operator on x plus 3. I want to get rid of the log base 2. So I do the opposite of log base 2, which is to take 2 and raise both sides of the equation. So 2 to the log base 2, 2 to the fifth. And now you see that this input is being operated on by log base 2, and then it's being operated on by 2 to the power of. So these kind of undo each other. They're inverse operations, and we're left with x plus 3 is equal to 32. So then we have x is equal to 29. So give the next problems a try, and I'll show the answers in 3, 2, 1. Now I just want to talk about something up here. Actually, let me just back it up a little bit. In this problem here, the first thing to do was not to take the natural log right away. It's kind of like this, where I have 2x squared plus 7 is equal to 10. The first thing I want to do is subtract 7, then I want to divide by 2, then I want to take the square root of both sides. So I want to work in kind of reverse PEMDAS order in a sense. So I want to add 7 to both sides, then I want to divide by 4, and then I want to take the natural log. And it's important to recognize that we do not want to take the log base 4e, because 4 is being multiplied times e. 4e is not the base of this exponent here. E is the base. 4 is being multiplied times e. Okay, again, just remember, you have cases down here where you need to check the solution back into the very original equation. You see some negative inputs into my log, which invalidates the solution. Okay, last principle, inequalities. Instead of equal signs, when we have inequalities, the nice thing is we do the exact same thing as equalities as long as the base is bigger than 1. So I'm showing here what I did, and I'm saving some steps. I'm not even showing all the steps I previously did. Since I have 2 to the power of x, I'm going to take log base 2 of both sides, and I know that it kind of removes the 2 right here, and so I just get x on this side. Log base 2 of 36 is my answer here. And I do the same for all the other problems, and I will show those in 3, 2, 1. Now I need to actually add to this. I didn't do a complete job. I need to also restrict x here to be greater than 0 because the input has to be greater than 0. Let's look for the other log case down here. I also need to make another restriction as well. In this case here, the input has to be bigger than 0, so that means x must be bigger than negative 9. And in the last case here, I do have a log. The input to the log must be greater than 0. X here is already constrained to be bigger than 0, so we don't need to add anything more to that one. I will leave this question to ponder just for you to think about. We'll talk about it more in class.